Hello everyone. Today I'm going to deliver a lecture on computational fluid dynamics. I'm myself Dr. Sourav Poddar, an assistant professor in the Department of Chemical Engineering, Department of Aldia Institute of Technology. So first we need to understand, or I will try to jot down my lectures for today with these basic slides that you can say so. One is what is CAE background, basics, followed by your what is CFD, where and why it is needed, and the fundamentals being involved into it, essentials, followed with the examples. So now, when we go down into the introduction of this subject, we see that we had various components being linked to it. So that components, what are there? What is computational fluid dynamics? Why and where we use CFD? What is the physics of the fluid that is being considered in the computational fluid dynamics? And now in basic preliminary courses you have learned Navier-Stokes equation, why it is an important parameter being used over here, why not others are considered right now, that I will try to explain in the later class. Then numerical gridization, so what it is all about, followed by the grids, boundary and numerical stuffs. So now on the initial slide, I have told you the role of CAE. The full form of CAE stands for Computer Aided Engineering. Is the broad uses of computer software to aid in engineering analysis tasks. So that means instead of calculating on large number of papers for a long period of time, if we have the codes being known to us, we can simply change certain parameters into it, and then we can simply justify that parameters, why it is being related to the whole aspect and why it is being considered, and based on that we can do the calculation on a very shorter period of time. But very simply saying, I must say that while we work with CAB softwares in your computer aided engineering, you observe that this kind of simulations takes approximately for a month to get converged. This is one aspect. So that means you can understand, if you have worked down with paper instead of a month, you can require a year. So we have summarized this whole aspect to a month, whereas a year long problem can be solved in a month. So what are the computer engineering, aided engineering software applications we can go for? The first one is your finite element analysis. When we don't have a limit of any object, we can limit it down and we can calculate it down. Then your computational fluid dynamics, that means the fluid that we want to study down, we will be consider it with your computational software tools. Then multi-object dynamics, that means we generally use in your process industries and other areas also, followed by the optimization. So this is the whole thing we generally talk about. These are the four areas. Software tools that have been developed to support these activities are considered as a CAE tools. For your computational fluid dynamics, you can think about your ANSYS or fluid software, whereas your multi-objective, you can think about aspect optimization, design aspect, or finite element analysis. You can think about MATLAB and other sophisticated analysis are there. But that is right now in my mind. These are the software names that are coming down into play. Now, why we generally require or we generally try to use this aspect? We generally try to use this aspect because in recent time, instead of investing any kind of money before large scale, we generally try to see it in computer whether it is a viable aspect or not. Based on that, we will try to analyze with a pilot plan scale whether this can be workable or not. then with the software analysis, with the pilot scale analysis, we generally go for large scale applications. So that's why this computer aided analysis became a major part right now in the world. Obviously, AI has came down into the play and taken some advantages and also disadvantages linked to it. So now we'll not go more details into it. We will try to see what is CFD. So, as the definition says, computational fluid dynamics, in short, we say CFD, deals with the solution of the fluid dynamics and heat transfer problems using numerical techniques. That means we will try to solve the flow of the fluid and the heat transfer that is being involved into it, and we will try to summarize the result. Now, CFD is an alternative to measurement for solving large scale fluid dynamical system. So, this kind of software is generally being used in your aerospace, mechanical, then the automobile, chemical, metallurgical, electronics, and even food processing engineering, industries. When this kind of software is being used in large scale across the world to large areas, you can say. So now how it is being used, that is an important aspect that you need to understand very simple. Why it is being used in aerospace? See that the aeroplanes generally have a structure. Now when they travel from one place to another place, they are either with the movement of the wind or against the movement of the wind. And the movement of the wind may be slower or greater than in that object. The aeroplane that we are talking about. So in that aspect, we need to create a motion so that if it is or the wind speed is low, or we need to create a pattern of the structure so that it can move with a greater speed rather than it is being obstacled by it. And in automobiles, what we observe, that is the shape of the vehicles that is being taking part, how it is. So over there you will observe the top of the vehicle will have some kind of an dome kind of a shape, so that when the vehicle is moving against the wind speed or for the wind speed, it doesn't get affected, and the person who is sitting inside will not feel any kind of a wind pressure from out inside. So that's why CFD came down into play for aerospace and your automobile industry. Now in chemical, what we will do? Chemical, we generally observes that how the fluid is being flowing in your pipelines and certain areas, how it is being walking down. So we generally do observe that this has a certain flow pattern being linked to it. So when we have a flow pattern linked with it, so we generally observe that, just a second, we generally, sorry for that, we generally observe that how the wind is being walking with the speed. So we see that uh, how it is being walking for a long period of time. To say the flow pattern movement, whether there is a back push of the chemicals being taking place or not, whether it is blocking the channel or not. So these are the areas we try to observe on. And from chemical we move down into biochemical. Then in electronics we generally see all these things, and then the food processing industry areas we generally do the same thing. Chemical, metallurgical, electrical, you can say this, all these areas we generally have this aspect. That means we generally try to see how the movement of the fluid is happening, what are the basic losses that is happening over there. We, in a non-ideal case, we will try to observe this whole aspects. So now if I go down into the CFD and we create a schematic view, we will observe that if I had a fluid problem, I can go with the physics of the fluid. Over there, we will use the Navier-Stokes equations. Now, as I'm using the Navier-Stokes equation, you will find that mathematics comes down into the play, and in physics, fluid mechanics will come down into the play. And fluid mechanics, along with mathematics coming down into play or creating a complicated expression, will always have to be solved. How we will solve it? We will solve it with a numerical method. And when we solve it with a numerical method, at times we observe they are not to be in a continuous form. They are in discrete format. And this discrete format requires, that is, grid. That means square block gridding has to be done. And as square block gridding is done, that means geometry is coming down again into the play. And these grids will be working with your programming language, that is your ANSYS, CF, your Fluent we will try to use down. And over there we will try to use computer programs, and then we will create a simulation result. And we'll have a comparison and analysis. How we are going to get the result, what results we got down is exactly relevant to us. So this whole schematic diagram tells that the fluid problem that we have, with the help of physics, mathematics, geometry, and your computer language, we will be saying whether it is working in a proper mode or not. So this is the whole aspects we will try to observe in the CFD class. So now, before going down into the details of the CFD class, you see that a figure is being given, and it shows that we had pre-processing, then we had computing, then we have post-processing. So pre-processing means creation of a physical model, and then we will try to create it in the computer, the same model that is known as the computational model. So that means we will be replicating that physical model to the computational model. And after replicating it down into the computational model, we will try to solve this whole aspect. And as we try to solve this whole aspect, so we will be having some visual images out of it that we need to analyze it down. And this is known as the result, that is the post processing. So for doing that, we will be using some software tools, either your ANSYS software or finite element method we will try to use down. So now this is the whole phase of this computational fluid mechanics is all about. And for doing so, while we are doing the computational part, we will be observing a iterative method. Like in your numerical analysis class you have done, that is iteration of a final process, and we got down a final result out of it. So that's why we will try to utilize this whole aspects, and we will try to see how it is coming down. So this is the whole part of your CFD is all about. So now the phases of CFD we have discussed in our class, and we see that there are three phases. One is your post processing, then we had computing, which we do with your supercomputers. Otherwise, in laptops, if you work for a month or so, the laptop will get slowed down. This happened with me also. So that's why I try to prefer a supercomputer. Then post processing results, and then visualizing the results, validating the results, analyzing the results, we try to do down in time. So this is the whole scenario we will try to observe that. Now, what is the definition of CFD, or what it is exactly we will try to see in this slide. CFD is the science of predicting fluid behavior. That means fluid flow. Fluid will flow anywhere, air is a fluid, water flowing through a pipe is also a fluid. So now as the fluid is flowing, so it has some heat transfer being linked to it, some masses being linked to it, change in the mass volume, And if it is changing in the mass, that means some kind of chemical reactions is being taking place. So when we talk about CFD, we had fluid flow, heat transfer, mass transfer, and chemical reactions being linked to it. And with all this, we create the complex equations and we generate the ultimate result out of it. So then, while doing it, we will be creating the governing equations of the fluid flow using numerical approach, and we will try to validate the result. So this is the CFD is all about. Now results of CFD analysis, the results that we got down after working for a month or a, so what we will try to do, we will try to conceptual studies of the designs that we got down, we will try to observe that, and we will try to observe what are the conditions we have applied to it. So after seeing all these conditions, we will try to modify the result and we will try to see what we have generated at the end. So then we will try to justify our results whether we have done it in a right way or in a wrong. That means instead of working in the lab, also we can do this software analysis, then go for lab experiments, and we can reach to a final results with the validated aspects. So this is what is computational fluid dynamics is all about. Next we will try to move down into why and where we use CFD. Why we use CFD? The first point says that simulation based results instead of build and test. So obviously instead of spending large sum of money, we can go for computer delivered methods and we can create an good aspect out of it, and most cost effectively we can work it out and more rapidly than with the experiments, because when we take a chemical reaction, we see that the chemical reaction initially might take hours to get started out, whereas if we work down with the computational methods, we will try to see that this thing will try to justify in a very short period of time. And CFD solutions provide high fidelity database for interrogation of fluid flow. So this is why we try to use this CFD concepts. Simulation of physical fluid phenomena that are difficult. At times we observe that when we work on large scale, we generally find it to be difficult. So what we try to do, we will try to implement all the physics, pattern, hazards being linked to it, scale simulation we can do over there. So that is the reason we use. Instead of doing it or spending large sum of money initially, we can walk down with the software and we can create a model on lab scale, then scale it up to the large scale with the conditions that are required in the large scale condition. All these parameters we can utilize over there and we can create a model in both the scenarios, and we can compare the model, and finally with the results that we got down, we can create the model slowly. That means if the model is a validated model, we can create it in the physical format. Knowledge and exploration of the fluid flow is the main important aspect of this CFD software is all about. Now you see, when we use a simulation software, the cost is very cheap according to the experimental one, which is an expensive one, and the time is very short, but the experimental is a long one. Scale can be of various type, like your small or middle or a large scale. Information all we can put down, all we can gather and we can put down. But in experiment at times what happens, certain parameters are not known, and then the reaction or the experiment that we are performing down can be invalidated at times. And this software simulated part can be always in a repeatable format, at times when we have a chemical reaction being taking place, it is not repeated. At times we have to repeat the whole experiment for days after days, years after years, in order to reach to the destination that we wanted. And security wise, obviously the software is safe and secure before going for a large investment. Some I have done with experiment and I got in some blasts. So obviously some dangerous situation can occur now. Now instead of that, if I work down with the software and create a model and generate a good aspect safely and then work it with the experiment, so that will be helpful for me to work down. So that's why we use CFD. So when this CFD was being started and why we started trying to use it. Computers, you know, that was built in 1950s, performed limited floating point operation per second. So from that time onwards, we tried to walk down, and in today's time, we got a total knowledge of the computer, and then we are trying to reduce the cost of all the industries. So that means computer became a major part, and that is why we tried to use computers over here, because in previous days we observed that computers, or when we have to store data or we have to transfer data from one place to another, we have to use some floppy drive, we used to say so. I think you were not acquainted with it. So that time we used to buy floppy drive, then came your CD, after that your DVD, after that came external hard disk, after that came small your pen drives, and after that microchips came down into it. That means the computer has drastically changed over the years. Their storage capacity, their computational speed capacity, they have changed, and that helps us to walk down with computers more effectively with this field, that is computational fluid dynamics. So where we can use computational fluid dynamics, aerospace we can walk down with. Now this figure I have shown you, you see this figure, I will explain it now. Then appliances areas, automotive areas, biomedical areas, chemical processing, havocs, and we can use hydraulics, marine, oil and gas, power generation, and sports. You see there are three figures, and each figure have a different zones. One yellow, then red, green, blue, all these zones. So what it is exactly? It is basically the temperature zones they are trying to bring down. So you see, for example, of this uh, plane. So the ones which are moving or exposed to the front zone are with red. Then with yellow, some the temperature change is light. Then with green, and the zones which are not totally affected with pink. So this color changes will help us to suggest how the movement is happening, what is the flow, where the flow is taking place, how the flow is taking place. So now, for example, the wing of this aeroplane, if I consider, the one which is exposed to the atmosphere straight up, that is exposed down. See the red, followed with orange, then yellow, then green, then blue. So this is the minimal part where or the majority of the function is less. The one which are the red zones, they have the maximum functions. So with this we'll stop over here. We'll try to see it on the next class. That's all for